600 years is the precise duration nature requires to decompose a single discarded tire. 1,500,000,000 units are currently being thrown away across the globe, forming vast black expanses of toxic waste that remain clearly visible from orbital altitudes. For several decades, these accumulations represented a persistent ecological threat, yet contemporary engineers have successfully converted this environmental liability into the black gold of modern infrastructure. Why is this specific transformation from poisonous waste into paving material so technologically advantageous? It only looks obvious to dispose of them as refuse, but in reality, incorporating this material creates roads that are significantly quieter, possess a lifespan that is doubled, and consume 10,000 tires for every single kilometer of pavement. The industrial sequence begins on a scale that surpasses standard human comprehension. One can notice vast territories covered by artificial hills that are dark, jagged, and imposing in their geometry. At first glance, the landscape resembles a post-apocalyptic environment, but the equipment gradually reveals that these are some of the largest reserves of untapped resources on the planet. Millions of these rubber mountains accumulate across the United States, Europe, and the Middle East. What previously functioned as a stationary cemetery for industrial residues has now been redefined as a primary harvest field for raw materials. Logistical operations behind this recovery process function with the absolute precision of an industrial symphony. This does not involve standard refuse trucks collecting random debris, but rather dedicated fleets of heavy vehicles equipped with high-capacity platforms and robust fastening systems. These units operate as vital arteries, continuously connecting maintenance centers, vehicle garages, and scrap depots to massive processing plants. The process is only gaining momentum. Every single tire is systematically removed from circulation before it can accumulate rainwater and serve as a biological breeding ground. Engineers view these spent casings not as waste, but as high-grade urban ore. Why is such intense effort expended on objects that were intentionally discarded? Inside every worn carcass exists a concentration of valuable materials, including elastic natural rubber, resilient synthetic polymers, textile fibers, and high-quality steel. For the recycling industry, a tire that possesses a value of only a few cents as scrap actually carries the potential to save billions of dollars in virgin raw materials. Extraction of these internal treasures remains a complex technical challenge. A tire is engineered to be virtually indestructible, designed specifically to withstand the friction of asphalt heated to high temperatures and the vertical pressure of trucks weighing 30 tons. To successfully recycle the component, technicians must overcome the very engineering principles that ensured its durability. Everything only gets more complicated at this stage. The primary obstacle in this mechanical confrontation is the internal steel skeleton that provides the tire with its structural integrity. 120 kilometers per hour is the speed at which a vehicle can navigate a sharp turn without the tire detaching from its rim. Why does the rubber remain firmly anchored despite such immense centrifugal forces? Within every tire lie braided steel rings, known as beads, which possess incredible structural strength and tension. But in the context of a recycling production line, this high-strength steel becomes a machine killer. It only looks obvious that a tire can be shredded directly, but in reality, these steel wires can shatter industrial blades, costing thousands of dollars. The process is only gaining momentum. If an intact tire enters a standard shredder, the steel will jam motor shafts and paralyze the entire factory's operations. The solution requires brute force applied with surgical precision. One can notice how the tire is positioned within a bead extraction machine, a heavy hydraulic hook driven by pistons capable of lifting the weight of several cars, penetrates the sidewall of the rubber. The equipment gradually increases the pressure until the internal components begin to shift. It seems simple, but this mechanical execution is the only way to safeguard the downstream equipment. A hook moves with the hiss of hydraulics as the metal and polymer are tensioned to their absolute physical limits. The force is so overwhelming that the robust structure of the tire twists, folds, and deforms as if it were made of thin paper. The process is only gaining momentum. Within seconds, the steel ring is pulled violently from the interior of the rubber casing. 2 kilograms of pure carbon steel are recovered from every single truck tire processed. This metal does not end up in a landfill. Instead, it is compacted into dense, heavy bales and transported to foundries. One can notice the bundles being loaded for shipment. There, the material will be melted down to reappear as structural construction beams or components for new vehicles. Meanwhile, the rubber carcass falls onto the conveyor belt, now deboned and stripped of its primary structural rigidity. It has lost its original shape, but gained a new purpose in the production chain. Everything only gets more complicated. Now that the steel is removed, the rubber is finally ready to face the blades that will grind it into fine powder. Before the destruction of the material begins, the rubber must undergo a mandatory purification process. The tire casing passes through enclosed washing tunnels. High-pressure water jets strike the surface to remove contaminants. The camera glides along the conveyor as the debris is washed away, ensuring that only clean material proceeds to the secondary crushing stage. The cleaned rubber moves forward along the line to meet the rotating blades. Thus, the material reaches the standard ready for the further stage. 100% of the embedded stones and debris must be extracted before the material advances. Why is this cleaning stage considered vital for the survival of the machinery? It only looks obvious that the rubber is ready for processing, but in reality, a single stone hidden within the tread could act like a projectile inside the shredder, causing catastrophic damage to the hardened steel components. One can notice how the equipment gradually clears the surface of any foreign objects. This ensures that only clean, prepared rubber enters the primary crushing chamber. Everything only gets more complicated as the material reaches the heavy machinery. Massive shafts armed with blades made of hardened steel alloy rotate at a slow but relentless pace. The sound here resembles a persistent industrial storm. One can notice how the blades bite into the thick casings with immense force. But this is just the beginning. A low rotation speed is a crucial technical secret in this specific environment. If the blades were to spin at a high velocity, the resulting friction would generate enough thermal energy to melt the rubber, turning the interior of the machine into a sticky and useless mass. By rotating slowly with devastating torque, the blades chew through the tire structure, slicing it into irregular fragments roughly the size of a closed fist. The process is only gaining momentum. These jagged pieces fall directly into secondary shredders. At first glance, the destruction seems complete, but in reality, the mechanical violence becomes even more refined at this stage. The primary objective now is to reduce the entire volume into fine crumbs. During this high-pressure transition, any remaining steel wire that survived the initial extraction is finally liberated from the rubber matrix. It is visible how the material layers move along the conveyor belts toward the purification zone. Giant magnetic separators positioned above the stream act with precision, pulling every metal fragment out of the flow while allowing only the organic material to pass. This separation occurs at a speed of several meters per second to maintain the volume of the output. The process does not end at this stage. The final product of this rigorous mechanical refining is known as crumb rubber, which reaches a specific granular consistency. This material leaves the shredding circuit, transitioning into a calm stage of the production chain. 2 millimeters. This is the precise maximum diameter of the black synthetic and perfectly uniform sand that remains after processing. One can notice how the giant tire has completely disappeared, replaced by tons of fine powder that has been rigorously sieved and classified by size. But for the complex chemistry of asphalt, this rubber is still considered raw material. Why must this material undergo further preparation before it ever touches the heat of the mixing plant? It seems like a finished product, but without additional processing, the integration into the road surface would fail. In reality, the engineering requirements at this stage move into an invisible territory where microscopic details dictate the lifespan of the highway. At first glance, the crushed rubber appears ready for use, but microscopically, every single grain is coated in a thin layer of moisture and fine dust. If this damp rubber were introduced directly into a tank of boiling bitumen, the water would undergo an instantaneous phase change into high-pressure steam. This would create internal bubbles and structural voids that would weaken the road from within, causing it to crack and crumble in only a few months. The infrastructure would essentially fail before the first vehicle even drove across the surface. Transition to the next level. To prevent this structural disaster, the granules are transported via conveyor into a colossal rotary dryer. The equipment gradually turns as a massive steel cylinder that rotates with a rhythmic motion, positioned at a slight incline to ensure the material flows steadily toward the exit. it is visible how the internal flights lift and drop the rubber as it advances through the drum. The process is only gaining momentum. Hot air, generated by industrial burners powered by natural gas, floods the interior of the rotating drum. This raises the internal temperature of the material to a range between 93 and 127 degrees Celsius. It is an intense but strictly regulated heat. If the temperature exceeds this threshold, the rubber will burn and permanently lose its vital elasticity. Conversely, if the temperature remains too low, the moisture will stay trapped on the surface. Everything only gets more complicated at these thermal limits. Infrared sensors monitor every centimeter of the drum's length, adjusting the intensity of the natural gas flames in real time to maintain equilibrium. As the rubber tumbles inside the cylinder, the water evaporates into the exhaust stream, and the surface of each individual grain becomes chemically active. One can notice how the dust is stripped away, leaving the material in a state similar to a dry sponge prepared to absorb liquid. We are effectively activating the material so that it can successfully bond with the liquid asphalt in the subsequent phase of the chain. The process is reaching a state of readiness. When the rubber finally exits the rotary dryer, it is hot, completely dry, and chemically prepared to absorb the bitumen. The material leaves the furnace, transitioning into a calm stage where its thirst for the binding agent will finally be quenched. Thus, the rubber reaches the exact standard required for the next stage of the manufacturing sequence. 160 to 190 degrees Celsius is the range within which the massive storage tanks maintain the liquid bitumen. Why fuse two materials that, at first glance, should never successfully combine? This process involves the integration of solid rubber with a thick black fluid that acts as the primary adhesive for roadstones. Bitumen behaves like a stream of dark lava, reaching temperatures significantly higher than boiling water and nearly matching the heat of an industrial deep fryer. The process is only gaining momentum. Automated injectors force dry rubber into this searing lava at a strictly calculated ratio, where the rubber component typically constitutes exactly 20% of the final volume. Inside the reaction tank, heavy-duty industrial agitators rotate ceaselessly to create a powerful vortex. One can notice how the equipment forces these two distinct materials into high-velocity collisions. But in reality, this is not merely a physical blending similar to preparing a culinary batter. It is a complex chemical reaction. Everything only gets more complicated. During 30 to 60 minutes of high-intensity agitation, a technical phenomenon known as swelling occurs. The solid rubber particles begin to absorb the lighter oils from the bitumen, gradually expanding until they have reached double their original dimensions. The consistency of the mixture thickens visibly, transitioning from a thin liquid into a robust, gelatinous mass. It is this specific transformation that grants the rubberized asphalt its high-performance characteristics. The rubber serves as a microscopic shock absorber embedded within the adhesive matrix. It renders the finished asphalt flexible, allowing the pavement to respond to mechanical stress. When a heavy truck passes over the surface, the road deflects slightly and then returns to its initial shape rather than fracturing. The material resists the degradation caused by the scorching sun and the freezing temperatures of winter. This creates a hybrid material capable of resisting the typical effects of aging. The process is only gaining momentum. Why is time considered the primary enemy once the mixing is complete? The mixture begins to lose thermal energy immediately, initiating a rapid race against the laws of thermodynamics. Workers discharge the rubberized asphalt into dump trucks with beds that have been preheated to a specific temperature. If the steel body of the vehicle remains cold, the mixture will adhere like permanent glue, rendering the entire load useless for paving. Exit temperatures are critical, maintained strictly between 132 and 149 degrees Celsius. Every single degree lost during the transport phase represents a step toward operational failure. The heavy trucks move at high speed toward the construction site, where the paving crew is positioned like a Formula One pit crew. A complex and high-precision machine known as the vibratory finisher receives the steaming cargo. It gets more complex further on. Internal mechanical augers spread the black mass with absolute uniformity across the entire width of the lane. Simultaneously, the heavy rear screed levels the material with millimetric precision. Digital systems adjust the thickness of the layer, usually setting it between 4 and 8 centimeters deep. One can notice how the steam rises from the fresh surface as the machine moves forward. It only looks obvious to lay the material, but the compaction phase is a dance of steel titans. Metallic rollers glide along the surface to smooth the top layer, while rubber-tired rollers exert pressure to knead the road. This action is necessary to expel trapped air bubbles and hermetically seal the internal structure. The material settles into its final form as it cools, completing the structural bond of the highway. 82 degrees Celsius is the critical threshold known as the death point for the asphalt mass. Why is this specific thermal limit so vital for the integrity of the highway? If the mixture cools below this level, the compaction process fails because the bitumen loses its binding properties. Instead of a seamless surface, the cold material simply fractures into disconnected fragments under the weight of the rollers. But in reality, success transforms the liquid mass into a solid rock structure within a few hours. The equipment moves with synchronized precision to ensure the surface is ready to support millions of tons of heavy traffic for decades. One can notice how the dark steam gradually dissipates as the density of the layer increases. But what happens when, after 20 years, 1,500 times is the distance the electrical wires currently installed across our planet could wrap around the Earth? Why does a slender metal thread, concealed behind common walls, manage to conduct energy sufficient to incinerate an entire city without melting itself? At first glance, it seems like a simple conductor, but in reality, its existence is a brutal journey of fire, immense pressure, and precision at a microscopic level. To illuminate a single room, the process must first descend into the deep shadows of the Earth. The narrative of an electrical cable originates not in the sterile silence of a laboratory, but within the deafening chaos of an open-pit mine. Engineering here performs a relentless mechanical assault against the very geology of the planet. One can notice the ground vibrating beneath heavy boots as the rhythmic pulse of industry vibrates through the bedrock. Why must engineers excavate vast mines of copper and bauxite that stretch for several kilometers like massive scars across the terrestrial crust? Surface deposits are rarely pure enough for direct use. These titanic machines operate without interruption through day and night cycles to access the metallic veins. The process is only gaining momentum. Engineers literally move mountains using the calculated violence of industrial explosives. Massive drills penetrate the solid rock to create dozens of deep boreholes that are subsequently packed with precisely calibrated detonating charges. When the signal is triggered, the Earth ruptures. Thousands of tons of rock fracture in a single millisecond, and dust slowly settles in clouds that momentarily obscure the horizon. This brute force is required to extract copper and aluminum from a geological sleep lasting millions of years. The scale of the operation increases as hydraulic excavators, standing as tall as 3-story buildings, move toward the debris. It is visible how their buckets, capable of lifting a passenger car with zero effort, scoop up the shattered remains. They fill a fleet of mining trucks that function as mechanical monsters within the pit. And this is not the limit. 300 tons is the weight a single vehicle can transport in one trip from the blast site. If a person stood beside one of these tires, the rubber would be twice their height. These steel giants move along the mine roads, hauling raw earth toward the primary crushing stations. There, boulders the size of sofas are fed into the machinery. The equipment gradually crushes the rock as if it were soft sugar, reducing massive fragments into smaller pieces for the next stage of refining. The material is ready to move to the next processing phase without haste. 950 degrees Celsius is the precise temperature at which the solid state of raw material begins its total transformation. Why must the extraction of metal involve such extreme thermal and chemical aggression? It would seem that simple melting might suffice to separate the elements, but without the application of specific electrolytic forces and intense heat, the chemical bonds within the mineral remain unbreakable, rendering the raw ore useless for industrial application. Mechanical brutality in the mining sector shifts toward the thermal intensity of the smelting facility. At first glance, the raw material appears to be nothing more than contaminated rock and pervasive dust. In reality, this stage functions as a calculated test of fire, designed to convert raw minerals into perfect conductors of energy. The equipment gradually prepares the furnaces to operate at levels of heat that exceed common technical limits. 1,742 degrees Fahrenheit represents the thermal threshold where the rock finally surrenders its structure. The process is only gaining momentum. In the specific case of aluminum production, the material extracted from bauxite enters specialized electrolytic reduction cells for a violent chemical restructuring. One can notice how the atmosphere shimmer around these units as colossal electrical currents are introduced. These currents possess a magnitude capable of instantly destroying any standard domestic electrical grid. Everything only gets more complicated as the electricity begins to physically tear the existing chemical bonds apart. The camera glides along the reduction tanks where the separation occurs. It is visible how the pure aluminum isolates itself from the waste, dripping steadily toward the base of the container. The liquid metal accumulates at the bottom of the tank as a bright, silvery fluid. A slow-moving stream of molten material forms a dense layer that must be handled with extreme technical caution. Purity levels of 99.9% are the mandatory standard for copper production. It seems simple to just melt the metal, but in reality, the requirements for electrical conductivity demand a much more rigorous approach. The copper must undergo several successive electrolytic baths. In these chambers, electricity functions as a microscopic filter that removes individual atoms of impurities. The process does not end at this stage. Any deviation from the required purity level is categorized as an unacceptable technical failure. Transition to the next level of quality control ensures that not a single foreign particle remains within the metallic structure. If even one microscopic impurity were to persist, it could lead to a fatal short circuit in power lines located hundreds of kilometers away. The metal finally achieves a state of total homogeneity as it prepares for the next phase of its industrial journey. Thus, the raw ore completes its transition into a refined material ready for casting. 150 tons of liquid steel, now purified and incandescent, are poured into heavy steel molds to begin the solidification phase. Why is the thermal transition managed with such strict precision? A simple drop in temperature is not enough to guarantee the structural integrity of the metal. If the cooling occurred naturally and unevenly, the internal crystal structure would become brittle and useless for industrial applications. The cooling process begins immediately upon contact with the mold. High-pressure forced cooling systems spray curtains of water directly against the metallic surface. One can notice how the outer shell of the ingot hardens instantly into a solid crust, while the core remains a soft, semi-liquid mass of heat. This creates massive solid ingots, heavy bars of metal that emit an intense orange-red glow from their internal thermal energy. But this block of metal cannot yet transport electricity to a household. It must undergo a total physical transformation to serve a functional purpose. The hot ingot, still radiating heat that creates a visible shimmer in the air, moves toward the rolling line. This equipment consists of hardened steel rollers that apply a pressure of several hundred tons to the material. One can notice the metal being forced between the rollers as they spin at high speeds, exerting immense mechanical force. The process is only gaining momentum. The thick, short block is crushed and stretched beyond its original physical limits by the rolling mill. Under this relentless pressure, the ingot is flattened and elongated until it transforms into a long rod, also known as a rebar, with a thickness of exactly 8 millimeters. However, 8 millimeters is still far too thick for the requirements of modern infrastructure. To create the delicate strands that form a contemporary cable, the material must enter the wire drawing stage. This is where engineering enters a microscopic scale. The metal rods are pulled through a sequential series of increasingly smaller openings known as dies. These dies are frequently constructed from industrial diamonds to withstand the friction and heat generated by the passage of the metal. One can notice the equipment vibrating slightly as the material accelerates. The speed of the line is staggering, with the metal racing through the workshop at tens of kilometers per hour. It is forced to become thinner, significantly longer, and perfectly round with every pass. From a heavy, thick rod, the steel is reduced to a strand finer than a human hair. This transformation is a sequence of controlled mechanical violence where the properties of the metal are reshaped by force. The equipment gradually pulls the strand through the final die, ensuring the diameter is consistent to a fraction of a millimeter. Thus, the steel reaches the standard ready for the further stage. From here, the transformation moves to the next phase of processing as the fine wire is coiled without haste. 1/1000th of an inch is the microscopic margin of error allowed during the continuous monitoring of this wire in real time. Why is such extreme precision necessary for a simple strand of metal? A dedicated laser system scans the surface constantly, and if the diameter deviates by even this tiny fraction, the automated controls adjust the mechanical tension instantly. The equipment gradually produces a finished strand that is bright and as smooth as a polished mirror. But this is just the beginning. It only looks obvious that the process is complete, but in reality, a hidden physical crisis exists within the material. The metal has been pulled, stretched, and forced through industrial diamonds, leaving its internal structure dangerously stressed. At first glance, the wire appears perfect, yet it has become rigid and brittle. If a technician attempted to bend the strand at this stage, it would shatter instantly like a pane of glass. It requires a specific thermal intervention to restore its properties. To heal the internal damage, the material is fed into specialized annealing chambers. One can notice how the wire enters these sealed furnaces, where every trace of oxygen is purged to prevent the metal from rusting or tarnishing during the cycle. The temperature rises with technical precision to exactly 600 degrees Fahrenheit. This heat is not intense enough to cause melting, but it provides the exact thermal energy required for the atoms inside the copper or aluminum to rearrange themselves. Everything only gets more complicated as the crystalline lattice, which was distorted and elongated during the drawing phase, begins to realign into a stable pattern. Internal tension evaporates as the molecular bonds settle into a balanced state. The process is only gaining momentum. It is visible how the metal maintains its outward appearance while undergoing a fundamental structural transformation within the heat-resistant chamber. Before this thermal reset, the wire was prone to immediate failure, but now it has become soft and incredibly flexible. The rigidity disappears entirely, allowing the strand to be bent, twisted, or coiled into tight loops without the risk of structural fractures. This invisible transformation remains vital to the integrity of the product. Without this calculated thermal psi, no electrical cable in the world would maintain its functionality under mechanical load. The metal leaves the furnace, transitioning into a calm stage. Thus, the wire reaches the standard ready for the further stage. 100 coils of shining wire are loaded into a massive industrial machine the size of a railway carriage. Why is the process of stranding considered one of the most mesmerizing moments in the entire industry? A single thin strand lacks structural integrity and is inherently fragile, but joining dozens of them together creates a metallic rope of immense strength. This transition from individual wires to a unified cable requires a mechanical ballet performed at high speeds. The body of the machine, known as the cage, begins its rotation at a constant velocity. One can notice how the spools dance in perfect circles, creating a silver vortex in the air as they spin. The equipment gradually pulls the individual wires toward a central point located at the nose of the apparatus. Here, the strands are twisted over one another with absolute geometric precision under the hiss of tensioners. But this is just the beginning. Engineers calculate the exact angle of this twist down to the fraction of a degree. It only looks obvious to wind the metal, but in reality, the tension determines the final utility of the product. If the twist is too tight, the cable becomes excessively rigid and consumes an unnecessary volume of precious metal. Conversely, if the winding remains too loose, the entire structure unravels during the installation phase. It is visible how the components move in a metallic blur. Everything only gets more complicated as the finished rope is wound onto the take-up reel. The process concludes this phase, opening the road to formation for heavy-duty industrial applications. One can notice the even layer of the cable as it settles onto the drum. The material is ready to move to the next processing phase without haste. 100% precision is the only threshold for success in this rhythmic and constant operation. Sensors monitor the mechanical tension of every individual wire within the assembly. Why is such microscopic vigilance necessary during the high-speed rotation? One might assume a single break is insignificant, but in reality, if a single strand thinner than a human hair snaps amidst this mechanical hurricane, the entire machine ceases movement in a fraction of a second. The process is only gaining momentum. What emerges from the far side of the rotating equipment is no longer a collection of loose metal strands. It is a unified conductor, possessing the flexibility of a fiber rope and the structural integrity of a solid steel bar. This component is now capable of transmitting the massive electrical currents that sustain modern infrastructure. At this specific stage, however, the bare conductor remains inherently lethal. It seems simple to handle, but in reality, direct contact with the metal while energized would result in an immediate fatal discharge. It requires a specialized armor to contain the energy. One can notice the bare metal conductor entering the extrusion line to receive its protective skin, known as insulation. In massive silver silos, tons of small plastic granules, consisting of special polyvinyl chloride or cross-linked polyethylene, wait in high-volume reservoirs. These granules resemble small white or transparent beads. Transition to the next level. The equipment gradually suctions these beads into a machine that functions on the principle of a powerful industrial-scale hot glue system. The plastic is heated until it transforms into a viscous and completely homogeneous paste. The equipment ensures the melt color and density are uniform throughout the chamber. It is visible how the metal wire passes directly through the center of a precision-engineered steel crosshead. The molten plastic is injected under high pressure around the metal core. The process resembles the encasing of a product, but executed with a tolerance measured in micrometers. Everything only gets more complicated as the layer of plastic must be perfectly concentric relative to the core. If the insulation is thinner on one side than the other, electricity can escape through the weak point, leading to catastrophic failures or the eruption of fires. As soon as the heated plastic makes contact with the cold metal, the entire cable assembly plunges into a long trough filled with circulating cold water. The thermal shock is immediate, causing the polymer to solidify and lock its molecular structure. The cable glides through the cooling bath as the transition from liquid to solid state concludes. The material leaves the cooling section, transitioning into a calm stage of the production cycle. 100% structural integrity is established at this stage, locking the protective form into its permanent state. Why is a single layer of insulation considered insufficient for the massive cables running beneath city streets? While a standard coating provides basic isolation, urban environments subject the conductors to extreme chemical exposure, oil seepage, and even the constant threat of gnawing rodents. Consequently, these heavy-duty lines receive multiple additional layers of reinforced sheathing to ensure long-term survival. Some specialized cables destined for the ocean floor are wrapped in heavy steel armor. One can notice how the metallic ribbons wind around the core to withstand the crushing atmospheric pressure of the deep sea. It only looks obvious that such a robust product is ready for immediate deployment, but this is just the beginning. The factory engineers do not rely on probability and instead subject the finished material to a sequence of destructive trials. Transition to the next level. Before a single meter of finished product is cleared for shipment, it must endure the rigorous conditions of the quality control chamber. The stakes during this evaluation remain exceptionally high. A catastrophic failure in these conductors represents more than a simple localized power outage. It could potentially lead to total energy loss in a critical hospital facility or a high-voltage fire within a metropolitan skyscraper. Therefore, the process begins with the high-voltage electrical stress test. Engineers discharge a current significantly higher than the levels the cable will ever encounter during its operational lifespan. They monitor the equipment for any sign of electrical leakage or structural weakness within the insulating polymer. This procedure functions much like overinflating a balloon to find its limit. If a microscopic flaw exists, the cable will rupture within the controlled safety of the laboratory environment. It gets more complex further on. Mechanical testing stations follow the electrical screening. Industrial manipulators pull and stretch the cable sections until they reach the absolute breaking point. This ensures that the bond between the internal metal and the external plastic remains inseparable under extreme tension. One can notice how segments of the cable are placed into specialized fire chambers. Here, the insulation is subjected to direct heat to verify if the material resists ignition or succumbs to melting. Other samples are simultaneously moved into cryogenic cooling units. This ensures the sheathing does not develop cracks or become brittle when exposed to the sub-zero temperatures of a harsh winter. Lasers ceaselessly scan the exterior surface to detect imperfections that remain invisible to the human eye. The process is only gaining momentum. High-energy X-rays penetrate through the thick plastic layers to confirm that the metal conductor at the center remains perfectly aligned. The equipment gradually maps the internal geometry without damaging the outer casing. From here, the transformation moves to the next phase of processing. Only the cable that survives every rigorous trial receives the official stamp of approval. Why is this final verification so critical? The product undergoes multiple stages of stress before it is deemed fit for service. This ensures that every millimeter of the conductor can withstand decades of tension. Only after this verification is the finished product wound onto massive reels made of timber or reinforced steel. One can notice how the mechanical arms rotate the spools with steady, calibrated precision to avoid uneven layering. Each individual reel is weighed, meticulously labeled, and prepared for transport. They are stacked in storage yards, appearing like giant coins from a civilization of titans, waiting to be unrolled into deep trenches, high utility poles, and interior walls across the globe. Everything returns to the starting point. 60 million kilometers of cable are produced annually. This represents a global industry that generates $200 billion every single year. One can notice how the sheer scale of production reflects the constant demand for energy and data. But this is just the beginning. The wires hidden inside walls are not merely segments of plastic and metal. In reality, each one is a survivor of a violent and complex industrial journey. It was born from a calculated explosion in a deep copper mine, underwent transformation in a chemical inferno, and was stretched through the microscopic precision of industrial diamonds. The process is only gaining momentum. The material was cured by intense heat, braided within a high-speed mechanical vortex, and subjected to the destructive forces of fire and high-voltage electricity. It represents one of the most underestimated pieces of engineering in human history. These cables serve as the invisible arteries of modern civilization. Without their constant presence, the heart of every city would cease to beat in a single second. The process does not end at this stage. The next time a light is switched on, the journey that made that simple action possible should be remembered. In the realm of heavy industry, even the thinnest wire possesses a massive technical history. Australia generates $90 billion by feeding the world, yet it faces an invisible collapse. Its soil is gradually transforming into red dust. Every year, 4 million hectares of fertile land die as the topsoil is carried away by the wind. One can notice the dust clouds rising over the horizon as the ground loses its structural integrity. When modern technology failed to provide a solution, salvation emerged from an unexpected source. Why did rotting piles of waste on farms become the primary defense against erosion? The answer lies in the unique physical properties of discarded material. Dirty wool, long considered a useless burden by farmers, became the only shield capable of preventing an entire continent from turning into an absolute desert. At first glance, it seems like refuse, but in reality, it acts as a biological anchor for the Earth. Everything only gets more complicated as the scale of the crisis expands. Welcome to the vast Australian continent. It is visible how the land stretches across more than 427 million hectares. This is a scale that remains difficult to fully conceive. For generations, this territory served as the granary of the Southern Hemisphere, functioning as a massive agricultural machine. The equipment moves across these plains with relentless frequency to maintain the cycle of production. From here, the transformation moves to the next phase of environmental processing. 60% of the soil's organic matter has been lost after decades of intensive agricultural exploitation. Why is this specific concentration of biological material so vital for the survival of the Australian landscape? One might assume that soil is merely a structural medium for roots, but in reality, organic carbon acts as the essential fuel and biological adhesive that preserves the Earth's structural integrity. Without this critical component, the ground loses its natural ability to retain moisture and cohesion, transforming from a nutrient-rich sponge into sterile, loose dust. This ecological decline has reached a critical threshold across the continent. In the span of only 14 years, the vitality of the land in key regions such as New South Wales has plummeted to levels that threaten the nation's status as an agricultural superpower. It is visible how the Earth begins to crumble when its chemical and biological bonds are stripped away by overfarming. The process is only gaining momentum as the landscape shifts from a productive asset into a fragile, eroding surface. One can notice the arrival of an environmental apocalypse when the seasonal droughts descend upon these vulnerable territories. The wind does not simply move sand across the horizon, it physically removes the foundational layers of the future economy. In certain high-risk sectors, wind erosion strips away up to 1.8 tons of soil from every single hectare on an annual basis. At first glance, the air seems filled with simple dust, but in reality, these storms act like invisible fleets of transport vehicles hauling the land's fertility into the depths of the ocean. 6 million hectares of territory are currently categorized within the red zone. This classification indicates an extreme risk of erosion that threatens to render the terrain permanently uninhabitable for vegetation. Another 3.2 million hectares are actively collapsing due to severe water degradation, which further liquefies the remaining topsoil and washes it away. The scale of the destruction suggests a silent industrial-scale removal of the continent's most precious resource. The equipment of modern farming continues to move across fields, where the ground is literally disappearing beneath the treads of the machinery. This is not merely a localized crisis of production, but a fundamental breakdown of the geological and biological systems that sustain the industry. The transformation moves toward a state of total depletion as the landscape loses its capacity to support life. The soil reaches a state of exhaustion, marking the end of its traditional productive cycle. 200,000 tons of low-grade wool accumulate on Australian farms every single year. Why is this mountain of organic material gathering in barns instead of entering the global market? One might assume that such a vast resource would find immediate use in the textile industry. But in reality, this is not the fine fiber used for high-end garments, and the global demand for raw wool has shifted so drastically that the material has transformed from a source of wealth into a massive logistical burden. The process of decline is only gaining momentum. Families who have cultivated the same ancestral land for generations are now abandoning their homes as the soil cracks, dries, and eventually dies. It is visible how the earth loses its structural integrity, becoming unable to hold even a single drop of moisture for the crops. Agricultural infrastructure, valued at billions of dollars, literally trembles on foundations that crumble into fine gray dust. The country desperately required a technical miracle to halt this economic and environmental hemorrhage. It only looks obvious that a dying landscape needs water, but another national industry was simultaneously drowning in its own excess. Australia was once recognized globally as the undisputed kingdom of wool, where the merino sheep was synonymous with white gold. Annual exports frequently exceeded $4 billion, providing a stable backbone for the rural economy. However, the global market underwent a fundamental transformation that saw the demand for raw fibers plummet. Consequently, the prices for raw wool collapsed, turning a former symbol of national prosperity into a waste management crisis. One can notice how the barns overflow while the fields outside remain barren. Projections for 2024 indicate a further production drop of 12% across the sector. Factories have ceased operations, and established trade routes have come to a complete standstill. Despite this industrial paralysis, the sheep do not stop growing their fleeces, leading to a grotesque accumulation of biological waste. This creates a sharp contrast between the starving, desiccated land and the mountains of unusable fiber sitting idle in storage. The equipment remains silent in the closed processing plants while the wool continues to pile up. Everything only gets more complicated as the quality of the stored material degrades over time. This surplus now represents the second half of a perfect storm, where two separate crises begin to converge into a single industrial challenge. From here, the transformation moves to the next phase of processing to find a solution for both the dying soil and the wasted fiber. 3 to 5 years is the exact duration required for a single discarded fleece to decompose naturally when left exposed to the elements. This biological stubbornness transforms what should be a natural byproduct into a massive logistical nightmare for farmers. One can notice how gigantic piles of fibrous material accumulate across the landscape, left to rot slowly under the alternating cycles of intense sun and heavy rain. Why is this organic matter treated as an unbearable financial burden? To the eye, the accumulation looks like a simple waste management issue, but in reality, the disposal costs are so high that they threaten the economic stability of agricultural operations. Farmers cannot easily incinerate these mounds, nor can they bury them without violating strict environmental regulations. It seems simple to just let the material sit, But the reality is a cycle of constant loss. While these mountains of complex proteins sit stagnant, the surrounding soil only a few meters away frequently lacks the necessary nutrients and physical structure to remain fertile. This creates a stark contrast between a toxic burden of waste and the desperate need for land enrichment. But this is just the beginning. The transition from a waste problem to a technical solution did not occur through the use of heavy industrial machinery or massive excavations. Instead, the turning point took place within the controlled environment of a silent laboratory. Scientists shifted their perspective, analyzing the residual wool not as a discarded textile, but as a sophisticated biological material. At first glance, a single fiber appears insignificant, but in reality, its microscopic architecture is a masterpiece of natural engineering. One can notice under high magnification how each strand is encased in keratin scales, which are meticulously overlapped like tiles on a high-end roof. Everything only gets more complicated as the functional purpose of these scales is revealed. Unlike a standard roof designed to repel all liquid, these keratin layers act as intelligent gates that regulate the movement of water. The equipment gradually reveals that these structures allow the fiber to absorb and retain immense amounts of moisture. The process is only gaining momentum as researchers realize the potential of these moisture-trapping capabilities. The wool manages to hold significant volumes of liquid within its internal core, while the surface remains technically functional. The material is ready to move to the next processing phase without haste. 100% of its own weight in water is the volume this material absorbs, but the physical reaction goes far beyond simple retention as the fibers begin to swell. Why does this expansion of the wool structure matter so much for the agricultural environment? At first glance, it looks like a simple increase in mass. But in reality, as the wool expands, it undergoes a physical transformation of its shape, creating vital microscopic air pockets within the earth. The process is only gaining momentum. This mechanical change creates necessary space in the landscape, providing a solution for the compacted and suffocated soil of Australia, which desperately needs to breathe. One can notice how the wool acts as a biological pump, forcing oxygen into the deep underground layers. It does this effectively without the intervention of heavy mechanical plows that typically fracture and destroy the delicate internal structure of the terrain. Initial testing conducted across the regions of New South Wales produced results that were nothing less than shocking to the research teams. Investigators distributed a thin, uniform layer of this previously discarded wool over severely degraded land surfaces. Sensors embedded in the ground began to record data points that appeared statistically impossible during the first weeks of observation. Surface evaporation, the primary adversary in an arid climate, dropped by exactly 35%. Water that would normally vaporize into the scorching atmosphere remained trapped within the soil profile, guarded securely by the interlocking wool fibers. Everything only gets more complicated as the biological transformation begins. The true miracle observed was not merely mechanical, but deeply biological in nature. Where the wool was present, the camera glides along a landscape where life rapidly returned to the parched earth. Microbial density, representing the invisible architects of soil fertility, exploded by 30 to 50% in a duration of only a few months. The wool was not just holding moisture, it was actively feeding and sheltering an entire subterranean ecosystem. In specific test fields located in Queensland, soil that once possessed the hardness of red concrete began to soften and become friable. The process is only gaining momentum. One can notice the color of the earth shifting as the life cycle restarts and the ground regains its natural health. It only looks obvious to distribute the raw material, but a significant practical problem remained for the engineers. One cannot simply throw raw, untreated wool onto an open field and expect to achieve uniform or predictable results. The fibers tend to tangle into unusable masses, blow away with the desert winds, or clog the intake systems of heavy machinery. To scale this solution for industrial use, the raw nature of the material required a calculated transformation. The material is ready to move to the next processing phase without haste. 900 kilograms of agricultural pellets are produced from every single ton of waste wool processed in the industrial plant. The transition to the industrialization phase requires the deployment of a specialized production line to convert discarded biological material into a high-value soil amendment. Why is a new manufacturing architecture necessary for such a common byproduct? At first glance, the raw material appears to be nothing more than dirty, tangled fibers unsuitable for use. But through mechanical processing, this waste is fundamentally restructured into a dense energy source for vegetation. Industrial shredders receive the matted wool as it is launched into the grinding chambers. One can notice how high-resistance steel blades tear through the fibers at high speeds, reducing massive heaps of residue into a coarse and uniform powder. The process is only gaining momentum at this stage. Immense pressure and thermal energy are applied as the shredded material is forced through precision-engineered steel dies. The equipment gradually compresses the loose powder until it undergoes a physical phase change. The result is not a textile, but a hard, dry, and extremely dense granule known as a wool pellet. It only looks obvious that these are simple pellets, but in reality, each small cylinder functions as a biological water battery. The pellet remains dormant when buried in parched earth, showing no activity in the absence of moisture. It gets more complex further on once the environmental conditions change. The pellet awakens the moment irrigation systems are activated or rainfall reaches the soil. It is visible how the keratin core expands rapidly, greedily absorbing liquid and locking it within the fiber structure. When the Australian sun increases the ground temperature and dries the surrounding surface, the granule performs the inverse action. It releases the stored moisture with calculated slowness, delivering water drop by drop directly to the root zones of the plants. Everything only gets more complicated when calculating the total impact on the ecosystem. Soil moisture retention increases by a margin of 25 to 40% compared to untreated land. This shift allows the farmer to reduce irrigation frequency and conserve liquid resources. But this is just the beginning of the pellet's function. Nitrogen, sulfur, and carbon are released into the earth as the material undergoes a slow decomposition process over several months. This is not a synthetic chemical that risks burning the delicate root systems of the crop. Instead, it provides a steady and natural supply of nutrition as the keratin fibers break down. Transition to the next level occurs when analyzing the financial dynamics of the factory. Economic transformation mirrors the biological efficiency of the process. Waste that previously required capital for disposal suddenly possesses significant market value. The factory output remains high, yielding 900 kilograms of finished product for every 1,000 kilograms of raw waste wool introduced to the grinders. Thus, the steel components and mechanical pressure turn a liability into a stable resource for the agricultural sector. 3 times higher is the economic value of this processed material compared to the initial raw wool. In the state of Victoria, a modern gold rush has effectively reignited across the industrial landscape. More than 40 startup companies emerged within the span of a single year to capitalize on this transformation. One can notice how the heavy machinery operates with a constant mechanical hum, converting what was once considered industrial waste into a viable biological resource. But this technological revolution did not remain confined within the Australian borders. It crossed the vast expanse of the ocean and established a new and entirely unexpected purpose within the United States. Why did this technology find such a specific and futuristic symbiosis in North America? The expansion of the industry required a new environment to prove its versatility. In the regions of Texas and California, the ongoing energy transition is currently blanketing the desert floor with millions of individual solar panels. These are vast fields of glass and silicon that extend toward the horizon as far as the eye can reach. But these massive solar power plants face a relentless natural adversary in the form of wild vegetation. If the grass is allowed to grow beyond a specific height, it physically obstructs the sunlight and significantly reduces the total energy output of the facility. The previous solution to this problem was fundamentally brutal and inefficient. Teams of workers equipped with gasoline-powered grass cutters and aggressive chemical herbicides performed the maintenance manually. This method proved to be expensive and hazardous for the sensitive photovoltaic panels while being ecologically disastrous for the surrounding soil. Stones would frequently fly from the rotating blades and shatter the expensive glass surfaces. One can notice how fine dust clouds would rise to coat the precision sensors, further lowering their efficiency. It only looks obvious to use mechanical means for maintenance, but in reality, the risks outweighed the benefits. It was at this critical juncture that a brilliant alternative was conceived. The plan involved the total replacement of heavy maintenance machinery with flocks of grazing sheep. This gave birth to the practice known as solar grazing. The hard data confirms that nature often acts as the superior engineer in complex environments. Sheep function as autonomous grass cutters, characterized by high operational precision. They move easily beneath the low-slung metal support structures without the risk of severing electrical wires or launching stones into the glass. The camera glides along the rows where the animals graze without emitting any exhaust gases into the atmosphere. The scale of the impact is massive. Solar farms that integrated these grazing flocks recorded a total reduction in the application of chemical fertilizers and herbicides starting in September of 2017. The process is only gaining momentum as more facilities adopt this biological maintenance strategy. Molten logic meets organic efficiency, and the material cycle reaches a point of sustainable balance. 150% faster growth is the hidden benefit found within the cool shadows of the solar arrays. Why do the photovoltaic modules act as more than just energy collectors? While the panels generate power, they simultaneously shield the livestock from the scorching intensity of the sun and protect the underlying earth from direct thermal radiation. Grass protected from immediate evaporation thrives, expanding its biomass 2 to 3 times more rapidly than in open fields. The sheep consume this lush vegetation and transform it into natural manure. This process fertilizes the soil and sustains a continuous biological cycle. One can notice how the ground beneath the panels, instead of degrading into a sterile wasteland, gradually recovers its complex biodiversity. It is visible how the soil moisture remains trapped in the earth, fueling a regeneration of the local ecosystem. But this is just the beginning. Professional grazing teams represent a newly emerged technical profession within the renewable energy sector. These specialists utilize advanced software to meticulously map the movements of the flocks across the facility. This ensures that every square meter of the solar station is naturally mown by the sheep at the precise moment required for optimal maintenance. Everything only gets more complicated as high-tech energy production merges with ancestral agricultural practices. The trajectory of wool serves as a definitive lesson in technical humility for modern engineering. At first glance, it seems simple to design complex machinery to save the soil, but in reality, the solution was already present in the form of organic waste. From the Australian continent on the brink of exhaustion to the high-tech solar installations of Texas, a material once discarded as refuse has been redefined as a guardian of the terrestrial environment. The process is only gaining momentum. These wool pellets and roaming flocks are not merely focused on the production of fiber or meat. They are actively constructing a biological shield against the onset of drought. The equipment of nature proves that in a world of finite resources, the very concept of waste is merely a failure of human imagination. Transition to the next level. Perhaps the survival strategy for climatic shifts does not involve the construction of larger machines. It involves learning to utilize the microscopic tools that natural evolution has perfected over millions of years. The fleece that traditionally shields the animal from the cold has been repurposed into armor that protects the planet from rising heat. One can notice the physical shift in the landscape as the wool integrates back into the earth. 5 meters is the length often reached by the Burmese pythons that were once considered the untouchable kings of the Florida Everglades. These biological machines were believed to exist without any natural predators. It seemed obvious that neither human traps nor the forces of nature could halt these apex predators. But that perception changed in the deep swamps during a morning patrol. The team discovered the remains of a 45-pound alpha male, identified as Loki. The body was found brutally destroyed and missing its head, obscured beneath a thick layer of pine needles. This sudden shift in the predatory hierarchy indicates that even the most dominant biological systems remain vulnerable to environmental variables. The investigation into the cause of this neutralization reveals the harsh reality of the local ecosystem. Thus ends one of the key stages of observing the invasive species' impact on the terrain. 30,000 to 300,000 biological units are currently estimated to be operating within the vast hydraulic systems of the Everglades. Why did this massive population explosion occur so rapidly in the Florida landscape? The answer lies not in a gradual migration, but in a catastrophic failure of industrial containment that occurred decades ago. Florida had transformed into a global center for exotic reptile breeding, But the year 1992 brought a physical force that the infrastructure could not withstand. Hurricane Andrew, a storm of Category 5 intensity, acted as a giant hammer against breeding facilities. The destruction of these structures released hundreds of hatchlings simultaneously into the wilderness. At first glance, the release of small reptiles might seem manageable, but in reality, it triggered a total war between nature and an invasive predator. This event served as the definitive turning point for the ecosystem. One can notice how the landscape shifted from a controlled environment to a chaotic battlefield. The anatomy of a Burmese python functions as a miracle of predatory efficiency and heavy engineering. Its jaw is not a simple mouth, but an expandable loading system capable of opening to a width of 25 centimeters. This is equivalent to the diameter of a large dinner plate, allowing for the intake of massive biological cargo. Scientists have documented these organisms swallowing entire deer weighing 35 kilograms. Such a mass defies standard physical expectations for a predator of this size. The process is only gaining momentum. Internal engineering within the reptile is even more complex than its external structure. Once a colossal prey item is ingested, the body enters a state of metabolic superproduction to process the fuel. The heart physically increases in size by 40% to facilitate the necessary blood flow for rapid digestion. Digestive enzymes multiply by 40 times, turning the organism into a living furnace that dissolves bone and tissue alike. Everything only gets more complicated as this voracious mechanism impacts the surrounding environment. The effect on the ecosystem is comparable to a factory that consumes every available resource in its vicinity. It is visible how the natural balance shifts under this relentless pressure. In areas dominated by these predators, populations of raccoons have collapsed by 90%. Statistics show that 99% of opossums have been effectively eliminated from the local map. The natural water filtration system of North America began to fail under the weight of these biological invaders. It only looks obvious that the battle for the wetlands was lost to the pythons. But as the system reached a breaking point, a specific flaw in the biological architecture of the invaders began to emerge. Nature found a weakness in the seemingly perfect design of the predator. The struggle for dominance in the Everglades continues as new variables enter the equation. This phase of the environmental crisis concludes with a shift in the survival strategy of the local species. 35 pounds is the approximate maximum weight of a bobcat, yet this feline successfully neutralized an opponent twice its size. This predator, known as Loki, was no ordinary reptile, but a Judas snake, a healthy and powerful male equipped with a sophisticated GPS tracking transmitter by scientists to infiltrate the population and expose the location of breeding females. Why did a signal from such a formidable predator suddenly cease in the middle of the wilderness? The answer lies in a calculated strike that defies the typical logic of mass and physical strength. When researchers reached the final coordinates transmitted by the device, they did not find a bear or a human hunter at the site of the kill. Evidence from trail cameras and forensic analysis confirmed that a bobcat had successfully engaged and killed the heavy python. At first glance, such a confrontation seems impossible given the disparity in weight classes. But in reality, this was not a singular occurrence, but the opening stage of a tactical insurgency within the ecosystem. The process of behavioral evolution is only gaining momentum as the local fauna begins to adapt to the invasive presence. In the Big Cypress National Preserve, automated monitoring technology captured what ecologists now describe as a real-time shift in predatory strategy. One can notice how a bobcat systematically unearths a python nest with its claws. It does not merely consume the eggs for sustenance. The feline crushes the shells and hides the remains under soil and debris, performing a calculated operation of sabotage designed to eliminate the future generation of its cold-blooded enemy. Everything only gets more complicated as the scale of the conflict increases. Days after the nest raid, the same feline engaged a female python weighing 50 kilograms and measuring 4 meters in total length. In a combat scenario where a lapse in movement lasting only 1 second results in death by constriction, the bobcat utilized superior agility to evade the snake's strikes and deliver its own. The local wildlife, which previously retreated before the mechanical efficiency of the pythons, has discovered that these apex invaders are vulnerable. Transition to the next level of the food chain occurs as the smaller predators learn to topple giants. While the terrestrial war gains new combatants, the ancient lords of the wetlands are reclaiming their territory in the dark waters. American alligators, protected by armor refined over 7 million years of evolution, have begun to intercept the snakes with increasing frequency. These are not minor skirmishes, but high-velocity collisions of biological titans. The physics of these encounters is characterized by brutal mechanical forces. An alligator possesses one of the most powerful bite forces recorded in the animal kingdom, measured in thousands of pounds per square inch. One can notice how the water churns as the alligator locks its jaws onto the midsection of the python. The predator initiates a death roll, spinning its entire body mass with violent momentum. The torsional force generated by this rotation is sufficient to shatter bone and tear through the reinforced skin of the reptile. The struggle in the swamp reaches a point of total physical destruction. This concludes the observation of the current territorial shift within the marshland environment. 114% of monitored pythons meet their end within the armored stomachs of these apex reptiles. This biological interaction functions as a definitive zero-sum game where the stakes are absolute. Why is the size of the prey so critical in these aquatic confrontations? If a python exceeds a specific physical threshold, the alligator may perish during the ingestion process. But if the alligator secures the victory, the invasive predator is converted into biological fuel for its conqueror. The impact of the strike is as sudden as a gunshot. One can notice how tracking data reveals the frequency of these lethal encounters in the submerged environment. But the threat to the invasive species is not limited to the murky waters below. The process is only gaining momentum as the entire ecosystem responds to the intruder. The airspace above the Everglades has effectively transformed into an exclusion zone for juvenile pythons that have not yet reached their full size. Birds of prey, including bald eagles and great horned owls, apply a devastating level of mechanical force from above. It is visible how they dive with aerodynamic precision to intercept their targets. It only looks obvious that the birds have the advantage, but in reality, it is the specialized physics of their talons that ensures the kill. 220 newtons of pressure is the force an owl's talons can exert upon impact. These appendages function as biological hydraulic presses designed for total structural failure of the prey. The equipment of the predator is capable of puncturing vital organs in a fraction of a second, ensuring the intruder is neutralized before it can retaliate. Everything only gets more complicated as the pythons grow, yet in these early stages, the mechanical power of the raptors remains a dominant force. The biological pressure remains constant across the entire landscape. This concludes the current phase of the environmental struggle as the hierarchy of the wetlands reasserts itself.